conductivity, it also can dissipate tensile strength. Well, if you look at all of the mechanisms that a conjugated polymer goes through in order to dissipate tensile strength, chain elongation, chain pullout, chain scission, crystal breakage, molecular rotation, we see that all of these processes are reversible. So once a conjugated polymer exhausts all of these options, essentially what happens is that the material then begins to mechanically fail, which we can visualize as crack formation within the material. So the fundamental research question for my dissertation was, what if we then incorporate reversible dynamic interactions into conjugated backbones in order to direct the self-assembly and act as sacrificial bonds? So in order to test out this strategy, you need a model system. And the conjugated polymer that I use throughout my tenure as a graduate student is DPP-based polymers, which we use because of their great optoelectronic properties, as you can see from the fluorescence on the right here. And the dynamic interaction that I used for my dissertation was hydrogen bonding, which we selected for its modular nature and the ability for it to form spontaneously. The objective of my dissertation is then to develop a rational structure-property relationship and establish design rules for the preparation of highly performant and robust conjugated polymers. So using hydrogen bonding to elicit stretchable materials has been done previously and famously before in the BAO research group, where they incorporated this pyridine dicarboxamide conjugation break spacers into DPP polymers in order to form a molecularly stretchable conjugated polymer. The problem is, as you increase the ratio of this hydrogen bonding stretchable block, you ended up with an associated decrease in the electronic properties. So our strategy was then, what if we, instead of incorporating it as conjugation break spacer, we can modify the solubilizing side chains to avoid breaking conjugation and maintain the electronic properties. And we chose amides as the motif of choice because of its moderate bonding strength. So to start with, the synthetic scheme, it's relatively simple. We just took 6-bromohexanoic acid, reacted it with thionyl chloride in the presence of hexylamine to form compound 1. We then appended compound 1 onto a DPP monomer using an alkylation to form compound 2, which we then brominated with NBS to form the organohalide ready for Stille polycondensation. We synthesized the polymers in varying weight ratios due to solubility of the hydrogen bonding block. So due to solubility, the polymers are primarily this DPP TBC block with this solubilizing side chain that incorporate these hydrogen bonding block in varying weight ratios. So as you can see, the weight ratios increase for P2 to P4 at 5, 10, and 20 mole%. And as a control to ensure that the properties that we were finding were from hydrogen bonding and not just simply from replacing this branch chain with a linear chain, we also synthesized linear analogs in the same weight ratios. And finally, we synthesized a reference that contains no linear chains at all, so it's just this block here, which we call P1. All the polymers had good molecular weights, or within the same range, and had narrow polydispersity indices, so that the properties we were seeing were from the hydrogen bonding and not from a molecular weight effect. So to start, we characterized the hydrogen bonding within these polymers, and to do so, we looked at the IR stretching frequencies between 3300 and 3400 to look at the NA stretching. And as you can see, with increasing hydrogen bonding, you get an associated increase in the intensity of the hydrogen bonding or the NH stretching signal. In addition, by comparison of the 0, 0, and 0, 1 vibrational peaks in UV-vis spectroscopy, you can get a measure of molecular aggregation. And with increasing hydrogen bonding content, you get an associated decrease in the aggregation, which is typical for polymers that incorporate these kinds of moieties. Finally, looking at the thin films, you can see that P1 to P4, all of them exhibit a fibrous morphology and a relatively smooth thin film surface. So finally, we looked at the electronic properties through OPET fabrication, and as we had hoped, we were able to maintain the electronic properties even up to 20 mole% incorporation of the hydrogen bonding block, which is in contrast to previous strategies where the electronic properties were decreasing as a result of incorporating this block. So the summary of chapter 2 is that we modify the solubilizing side chains to avoid breaking conjugation and maintain the electronic properties. Now we want to look at what effect these side chains have on the mechanical properties. So chapter 3 is investigating the stretchability and healing through side chain engineering. The goal of this chapter is to investigate the effects of hydrogen bonding side chains on the molecular stretchability of the synthesized polymers and determine whether these polymers were capable of healing. So measuring the mechanical properties of conjugated polymers is made a little difficult directly because we're dealing with very thin films. So instead of stretching the thin films directly, what we do is we transfer it onto a substrate for support as we do our stretching. So to do this, we process the thin film on a low surface energy substrate, which facilitates transfer onto a PDMS stamp, which we can then stretch and transfer onto another substrate for visualization under optical microscopy. And in this way, we can measure what's called the crack onset strain of these materials, which is the strain at which they begin to mechanically fail. As you can see, for polymer stretched to 50% strain, for P1, which is the reference without any linear side chains at all, you see that you have these large microscale cracks that propagate throughout the material. But for P2, P3, and P4, which incorporate hydrogen bonding, they all maintain their pristine morphology. So increasing the hydrogen bonding content appears to improve the stretchability. Looking at the control polymers at the same ratios, you see at 50% strain, we still have the appearance of these microscale cracks. So to further investigate the mechanical properties, what we did was measure the elastic moduli of these materials. So again, the elastic modulus is a measure of the material's stiffness, and we did so through film on water tensile testing. As you can see, with increasing hydrogen bonding content, you get an associated decrease in the elastic modulus. So the materials are getting softer as you increase the incorporation of hydrogen bonding, which we can directly correlate to the increased stretchability that I just showed. So to get an idea of the molecular level changes that are occurring as we strain the material, we did polarized UV vis spectroscopy measurements to determine the dichroic ratio. And for the dichroic ratio, for an unstrained sample at 0% strain, the ratio of light polarized perpendicular and parallel and perpendicular to the sample is 1, because your sample is isotropic. As soon as you start to stretch your polymer, the sample becomes anisotropic because the chains are beginning to elongate in the direction of strain. So your dichroic ratio then begins to increase. As long as this dichroic ratio increases linearly with strain, then your polymer chains are continuing to elongate as a response to strain, and your polymer is still stretchable. Once it deviates from linearity, essentially what happens is that your polymer chains are no longer elongating. So for P1, which is the polymer that contains no linear chains, you see that the dichroic ratio increases up to 75% strain, at which point it deviates. For P6, which is the polymer with 10% linear chains, you see the dichroic ratio increases to 50%, at which point it decreases. And then for P3, the hydrogen bonding polymer, you see that it continues to align even up to 125% strain. So essentially, the hydrogen bonding polymers continue to align at higher strain percentages due to its increased ability to accommodate strain. In order to look at how the hydrogen bonding was affecting the self-assembly in these materials, we looked at the grazing incidence wide-angle X-ray scattering, and then through GWAX, we can determine or measure the crystalline microstructure of these thin films. And through GWAX, we can determine the relative degree of crystallinity between different conjugated polymers. So for increasing hydrogen bonding content, you see that you also get a decrease in the relative degree of crystallinity of these materials, which means that we're actually having an increase in the amorphous content within these materials as well. Essentially what's happening is that we're transitioning from this very semi-crystalline morphology from P1 into the more poorly ordered but aggregating ideal morphology as you increase the amount of hydrogen bonding. So like for the dichroic ratio, we see that the anisotropy induced from stretching these polymers has important consequences for the properties that you measure. We decided to measure the electronic properties both parallel and perpendicular to the strain direction. So for a brittle conjugated polymer, what happens is that as you apply strain, cracks begin to propagate in the direction perpendicular to the applied strain. So if you imagine the strain direction is left and right, cracks begin to propagate up and down. So for a pair of electrodes that have the charge transport oriented parallel to the applied strain, cracks will propagate along the long axis of the channel length and disrupt the electronic properties. And you don't have the same concern for the perpendicular direction because this will have charge pathways between the cracks. So for this reason, conjugated polymers that are not particularly stretchable suffer more in the parallel direction than in the perpendicular. And from the results of the OFAP application, you see that for P3, the electronic properties are better maintained in the parallel direction as compared to P6, which is a 10% alkyl reference. So finally, we wanted to see if these hydrogen bonds could act as a vehicle for repair. And after a sequential solvent and thermal annealing process, you see that for P3, which is the hydrogen bonding polymer, you get a restoration of its initial morphology, as you can see from the optical microscopy images and AFM, whereas for P1, you see that the cracks remain unchanged. So the summary for chapter 3 is that the polymer showed an increase in amorphous content with increasing hydrogen bond incorporation and consequently an increase in stretchability, and the synthesized polymer showed some degree of healability after damage. So since intermolecular hydrogen bonds intermolecular bonds enhance mechanical properties, can intramolecular interactions do the same? Which brings me to chapter 4, molecular stretchability through backbone engineering. So interactions that planarize the backbone of conjugated polymers have been used previously to enhance both the electronic properties and the thin film morphology. So an example here is from Dai et al. That uses these sulfur-oxygen interactions along the backbone in order to improve the power conversion efficiency in organic photovoltaic cells. Another example is by Yum et al. That use these kinds of interactions to improve the crystallinity within the thin film. So following this, our design strategy makes use of a weak electrostatic interaction between sulfur and nitrogen and a pyrazine flanked by thiopene monomer. The reason why we chose this as a starting point is because of its facile synthesis and synthetic tunability. So as I said, the synthesis is rather simple. You just take 1,4-dibromo pyrazine, do a Stille coupling with thiopene, tributylstanyl-thiopene to form compound 1, which you then metallate and react with trimethyltane chloride to form compound 2 ready for Stille polycondensation. We then synthesize the polymer in high yields and a narrow polydispersity index. So looking at the theoretical calculations of the thiopene and the pyrazine, you see that the lowest energy conformation is where the thiopene sulfur and the pyrazine nitrogen are cis to one another. And it's more stable by approximately 0.5 kcal per mole, so a very weak interaction, which confirmed what we had expected. In addition, looking at the thin films, you see that it adopts a very smooth thin film morphology, and also it's highly crystalline based on the GLAX patterns, showing several higher order reflections in a class that compete. So given its superior thin film morphology, we would expect that it would also exhibit similar optoelectronic and electronic properties. So we synthesize a freely rotating benzene reference polymer to use for comparison. So looking at the UV vids, you see that comparison to the 0,1 and 0,0 peaks, the pyrazine-containing polymer has an increase in aggregation, as well as the spectrum is slightly redshifted, both of which we attribute to the increased polarity induced by this conformational law. In addition, when you look at the electronic properties through OFAP fabrication, you see that the pyrazine-containing polymer has a one order of magnitude higher field effect mobility, in addition to having a higher device resolution and also a lower threshold voltage. So since we had an increase in electronic properties, we want to see how the mechanical properties were affected. So for the benzene reference polymer, you see it maintains pristine morphology at 0% strain, but then cracks begin to form at 35% strain, and they get worse at 50%. But for the benzene, or for the pyrazine polymer, you see the pristine morphology at 0%. that it maintains even at 35%, with cracks only forming at 50%. In addition, we looked at the dichroic ratio, and you can see that for the pyrazine-containing polymer, the material continues to align even past where the benzene reference polymer no longer does, which we can correlate to the crack onset strains that we see here. So finally, we want to look at the electronic properties under strain, and again, looking at the parallel direction, the direction parallel to strain, you see that the benzene or the pyrazine polymer is better able to maintain its electronic properties. Its electronic properties compared to the benzene reference. The summary for chapter 4 is that we synthesize an intrinsically stretchable conjugated polymer using a weak electrostatic intermolecular interaction, and the resulting polymer is high-performing and has a moderate increase in stretchability. So we wanted to see whether or not we can enhance this weak interaction through hydrogen bonding, and how does it compare with the strategy in chapter 2 and 3, which is to say intermolecular side chain engineering. So for chapter 5, we took what we learned in chapters 2, 3, and 4 and applied it here. And to do so, we appended amide side chains onto the flanking piping units of both the benzene polymers, and we did this to compare the properties of the different binding modes. So theoretical calculations of the dihedral angle of this monomer shows that the theoretical energetic cost for breaking the hydrogen bond is approximately 5.5 kcal per mole, which is 11 times higher than the nitrogen-sulfur electrostatic interaction. So we were successful in making a stronger interaction along the backbone with energy that is on the same order of magnitude as moderate hydrogen bonding. And then we see that the intermolecular unit, as expected, doesn't have the same energetic cost. So the synthesis, again, is also pretty simple. We just take thiophenene 3-amine, react it with hexanoyl chloride in order to make compound 1. We then brominate compound 1 to form compound 2. We do a lithium halogen exchange and quench with trimethylene chloride to form compound 3, and then we do a Stille coupling with dibromopyrazine to form compound 4, which we then metallated and reacted with trimethylene chloride to form the organotin ready for Stille polykondensation. For synthesizing the monomer for P2, we took the compound 3, reacted it instead with dibromobenzene in order to make compound 6, which we then metallated again and reacted with trimethylene chloride to form the reference monomer. We then did polykondensation of both monomers in order to form P1 and P2 in similar molecular weights. So first, we wanted to characterize the different hydrogen bonding modes within the polymers. So for that, we turned to iris spectroscopy. So for P1, you see that the CO carbonyl peak is in the completely unbound state, which makes sense because the carbonyl peak is not involved in hydrogen bonding in this case, whereas the carbonyl signal for the intermolecular hydrogen bonding polymer is in the completely bound state. Looking at the NH stretching signal, you see that for both P1 and P2, they're both in the fully bound state. In addition, looking at the UV vis, you see that the intramolecular P1 polymer is redshifted compared to P2, which is due to the hydrogen bonding, bringing the pi conjugated backbone to greater alignment. The interactions along the backbone have consequences for the rigidity of the polymer, because interactions that planarize the backbone tend to make polymers more rigid. So in order to investigate this, we did small angle neutron scattering experiments. Through small angle neutron scattering, you can get a measure of the persistence length of a conjugated polymer, which is a measure of their chain rigidity. So as you can see, for P1, we have a persistence length of 135 angstroms versus P2, which is only 66, showing that P1 is much more rigid than P2. After that, we did measurement of the elastic modulus, and we found that surprisingly, even though P1 is more rigid than P2 based on SANS, it's actually softer as well, which gave us hope for potentially having superior mechanical properties as well. Looking at the thin film morphology, you see that P1 is much more fibrous than P2, as well as much more crystalline, based on GWAX and the relative degree of crystallinity. So then we went on to characterize the electronic properties through OFET fabrication, and to no surprise, you see that P1 has a 3 orders of magnitude greater charge carrier mobility than P2, which we attribute to the greater backbone planarity induced by the intermolecular hydrogen bonding. So finally, we wanted to look at the effects on the mechanical properties through crack onsite strain measurements and polarized UV vis spectroscopy. And you see for P1 versus P2, you have a pristine morphology from 0% strain. But for the intramolecular hydrogen bond, you see that cracks begin to propagate at as low as 10% strain. Whereas for P2, you still have a pristine morphology. And then P2 then cracks at 35% strain. Looking at the dichroic ratio, you see that P2 can continue to line past where P1 can. Because P1 stops aligning at the same strain as the alkyl reference and at a strain well before P2. So the summary for the final chapter is that intermolecular hydrogen bonding leads to superior device performance compared to intermolecular hydrogen bonding. And despite being softer, intramolecular hydrogen bonding does not lead to an improvement in the mechanical properties compared to the reference polymer, nor does it result in healability. So the summary for my work is that side chain engineering is an efficient approach to produce materials that incorporate H bonding without compromising the electronic performance, as we saw in chapter 2. Using intermolecular hydrogen bonding is better for stretchability and some healing, while intermolecular hydrogen bonding is better for enhancing electronic properties, as we saw in chapter 3 and 5. And intramolecular interactions can improve stretchability if the interaction along the backbone is weakened, as we saw in chapter 4. So the future outlook is we can use these materials as a semiconductor and fully stretchable devices, as well as investigate other modes of interaction along the backbone, for example, disulfide bonds. In conclusion, we created a novel strategy for designing molecularly stretchable and high-performance conjugated polymers, and we developed a rational structure-property relationship and established design rules for the preparation of highly performant and robust conjugated polymers. So finally, acknowledgements. I want to thank my friends and family, the whole lab group, past and present, faculty and staff, everybody in the department, and everybody in the faculty. Thank you for the past 5 years, as well as all of you for attending my defense this afternoon.
Okay.